Please start, Dr. Bikeswari.
Okay. Honorable President and Convener of Manipur Sakti, Professor Asa Gupta, Resource Person, Professor Mutum Shyamkesho Singh, Department of Life Science, Manipur University, faculty members of Manipur University, faculty members of different colleges, administrators, members of Manipur Sakti, and participants. Good evening to one and all. Today, Manipur Sakti, in collaboration with Seed Manipur, is celebrating Science Week. I, Biteshwari Khangimbam of Tamenglong College, on behalf of Manipur Sakti, will say a few words. I welcome you all full-heartedly on this occasion. I welcome Professor Mutum Shyamkesho Singh, Department of Life Science, Manipur University, for sparing his valuable time in delivering lecture on the topic Principle of Microscopy. I welcome all participants present here. I also welcome Professor Asa Gupta, President and Convener of Manipur Sakti. Microscopy is used to view objects or specimens such as cells in biological application which are too small to be seen with the naked eye. Microscopy is essential to evaluate the integrity of samples and to correlate structure with function. It helps in two independent functions of enlargement and improve resolution. So this Science Week is organized to discuss about principles of microscopy. Now, I request Dr. Angie Niru of Moirang College to introduce our resource person, Professor Mutum Shyamkesho Singh, Department of Life Science, Manipur University, to the participants.
A very good evening to one and all. Myself is Dr. Nero. Let me take this opportunity to introduce today's resource person. That is Professor Shyamkesho Singh. He has completed his MSc in botany from Aligarh Muslim University, Aligarh, and completed his PhD in Varanasi Hindu University, Varanasi. At present, he is serving as a professor in a department of botany, and till now he has guided many research scholars, published many good numbers of papers in international and national journals of repute, and his specialization is in mycology and plant pathology. He will be delivering a lecture on the topic of the basic principles of microscope with a special emphasis on light microscope. Today, we are very privileged to have you, sir, into our midst, and then let us listen to his talk. Thank you, sir. Thank you.
Thank you, Nero. And today, I'm going to give this one a brief lecture on the basic principles of the microscopy with special emphasis on the light microscopy. Professor Asa Gupta told me that many of the participants of this webinar are students of the graduate colleges. And he specifically requested me to give on the basic principles of this microscopy, which I have been teaching in my department for many years. And in today's my lecture, I'm not going to do all the new developments, the research findings, and not that one, but the very basics of the microscopy, and especially in the light microscope, for the light microscopes. So much and slide. think, Nero, I think it can be seen the slides. Hello?
Yes, sir, we can see the slide.
Okay.
We can see, sir. We can see.
Yeah. This one, the topic, as I have already told, I have told you that basic principles of microscopy. And first of all, I am giving this the simple this definition of our microscope. And a microscope is defined as a high-precision optical instrument or device that uses a lens or a combination of lenses to produce highly magnified images of minute objects or specimens which are too small to be observed by naked or unaided human eyes. However, this simple definition of a microscope does not hold good or true is in recent times, in recent years, a group of a very sophisticated and very powerful group, type of microscope, such as atomic force microscopy and then scanning tunneling microscopy have been manufactured and have been used. And these newer microscopes, which are based on the scanning probe microscopy, they are very different in their working principles with the other types of the classical types of the microscopes, like this one, light microscopy, and this electron microscopy. And then when we are talking about this one classification of the microscope, these microscopes are classified based on the source of illumination or their working principles. When we are taking the consideration of the source of illumination, then the microscopes can use the visible light spectrum, which has a wavelength between 380 to 740 nanometer. And under this group, there are light microscopes. That is the light microscope, which has two types. That is the bright field microscope and the dark field microscope, and then the phase contrast microscope, and then which use the visible light spectrum as a source of illumination. And when we are considering about this fluorescent microscope, the UV ray, which is not visible to our human eyes, is used as a source of illumination for the observation of the microscope of the specimen through the microscope. And in electron microscope, the electron beam, which is produced by the electron gun and focus on the specimen, the electron beam is used as a source of illumination. And in this electron microscope, there are two types. That is the transmission electron microscope, EM, and the scanning electron microscope, SEM. And then we are considering about this one, the classification of microscopes based on the working principle. The scanning probe microscope group, there are two types available in the modern science. That is atomic force microscope and the scanning tunneling microscope. And this group of microscope, their working principle is very different from the above group of microscope, which are classified based on the source of their illumination. And this one, when we have I will just briefly explain the working principle of these different types of microscope. In bright field microscope, light microscope, both this diffracted and as well as the undiffracted rays, means this diffraction is caused by the specimen to be seen through the microscope. Both of this group of light rays are collected by the objective lens, and the image of the object is formed against a dark background, and thus the name is given as bright field microscope. And in case of the dark field microscope, the object is illuminated by a ring of light coming in an oblique, this one, angle. And when there is no this one specimen in the microscope, the objective lens will not collect any this one light from the light coming from the this one condenser lens. But when there is a specimen in the this one microscope at the stage, microscope stage, then the light will be diffracted by the specimen, and that these diffracted light rays are collected by the objective lens and form the specimen and the image of the object, and the image is bright against a dark background, and thus the name this dark field microscope is given. Then in fluorescent microscope, the UV ray, which is not visible to our human eyes, is used for excitation of the molecules or compounds present in the this one specimen or object to a higher level of energy, and resulting in the emission of the visible light rays which have lower frequencies, and which can be detected by the human eyes. And this microscope, that is fluorescent microscope, is very useful in this one immunofluorescence microscopy. And in case of the electron microscopes, the two types, that is the transmission electron microscope and the scanning electron microscope. In case of TEM, the image is formed by the transmitted electrons, which transmits through the specimen, which are usually very, very thin. As this one, the electrons have very low penetrating power, and for this transmission electron microscope, we have, for the preparation of the samples, the objects or samples should be very, very thin or ultra thin, and the image is formed by the transmitted electrons. Thus, the name is given transmission electron microscope. And in case of the scanning electron microscope, the name is given the scanning because a very fine electron beam, which is known as the electron probe, which scans the surface of the object or specimen in a raster manner, and it is usually performed by using a scanning coil. And from the specimen surface, the reflected electrons and the secondary electrons, which are released from the molecules of the surface of the specimen, they are collected and form a three-dimensional image of the surface of the specimen. And in case of the the scanning probe microscopes, they do not depend on these optical rules and optical theories. In case of atomic, they are very different from the other microscope in their working principle. In atomic force microscope, as well as this scanning tunneling microscope, in both cases, both of this one. In case of the atomic force microscope, Again, it is used for examining the surface of a material or specimen. And this specimen is again scanned in a square raster manner by a very, very fine tip of a silicone chip. And the impulses released from this scanning process is collected to give the image of the specimen. And in the same way, in case of this one, scanning tunneling microscope also, it has the same this one process. It also scans the surface of the specimen, and here the scanning is done by a very fine tip, very fine tip of a metallic wire. And when this one probe tips of the metallic wire is brought to the surface of the object or specimen to a distance of few angstroms, and when the electric field is electric voltage is connected to either the probe or the specimen, then a small current is generated between the probe and the specimen, and this is known as tunneling current, and it gives the picture and the properties of the surface of the specimen to be observed by the scanning tunneling microscope up to the resolution at the level of individual atoms. Thus, this group of microscope, that is the scanning probe microscope, they are very powerful microscopes and having very high resolving powers or resolutions. Then when we come back to this one, light microscope, where I'm going to give more emphasis, then when we go to the basic definition of a microscope, if we examine the definition of the light microscope, this microscope has three important functions. That is the formation of an image of the object to be observed through the microscope, and then because this image, objects or specimens are too small to be seen by the human eyes, thus the image formed by the by the microscope of the object should be magnified so that human eye can observe them. Thus, the second important function is the magnification of the object image, and the third important function of this a microscope is the resolution of the magnified object image. Although this one in magnification we can achieve to almost any desirable magnification level by proper combining of the lenses, this magnification to some limit is only useful. The magnified image without resolution is known as empty magnification, and thus when a magnified image is observed by human eyes, then it should be identifiable, and the details of the image of the object should be resolved in a resolved manner. Thus, the resolution or resolving power of the microscope is also a very important function of the microscope. And in this, at this point, here comes the concept of the limit of resolution of a microscope. And in case of this one, formation of an image by a microscope of an object can be explained either by this one geometrical optics or physical optics. this geometrical optics explain the that one of focusing of the an image formation by the lenses used in the used by the microscope, while the geometrical optics and the physical optics explain the underlying principles of the contrast and the sharpness of image. Then when we come to this magnification, the function of magnification of the microscope, this magnification is the function of the magnifying power of the lenses used in the microscopes. And this again, this magnifying power of the lenses is depends on the focal length of the lenses. And the final magnification of an image by a microscope is equal to the multiplication result of the magnifying power of the objective lens and the ocular lens. Then when we come to resolution, and as I have already mentioned that limit of resolution is a concept giving the resolving power of defining the resolving power of a microscope. And this limit of resolution of a microscope can be defined as the minimum distance between two closely placed points or lines or two objects, and up to which the microscope can distinguish or identify them as two separate objects. As for example, the normal healthy human eyes at a normal viewing distance of 25 centimeter, it has a limit of resolution of approximately 0.1 mm. It means that it refers that two objects or 2 points or 2 lines which are spaced by 0.1 mm can still be identified by human eyes as 2 separate lines or 2 objects or 2 points. But if the distance between these 2 lines or 2 objects is lesser than 0.1 mm, then the human eye cannot identify them as 2 separate points or 2 separate objects. That is, the images of the 2 points or objects, they overlap to each other, and it is known as the unresolved image formation. And the numerical value of a microscope, it may be light microscope or electron microscope, is given by the relationship that is D or delta is equal to K, lambda, and NA, where this D or lambda is the limit of resolution, value of the limit of resolution. Then lambda is the wavelength of the illuminating ray. It is when we are using this visible light spectrum, then it will be the wavelength of the visible light spectrum. And when we are using the electron microscope, then the wavelength of the electrons, the value will be the wavelength of the electrons. Then another value that is NA is the numerical aperture of the objective lens plus numerical aperture of the condenser lens. And the K is a constant factor, and the value of 0.61 is taken for both light and electron microscopes. And then when the aperture of the condenser lens as well as the aperture of the objective lens, they are the same, then the equation of this limit of resolution is simplified, that the limit of resolution is equal to 0.61, that is the value of the constant factor, and the value of this lambda, that is the wavelength of the illuminating ray, and the numerical aperture of the objective lens. Means it is numerical value is not objective lens plus this that of the condenser lens. It becomes only the numerical value or numerical aperture of the objective lens. And then wavelength of this visual light spectrum having this 7 different types of colors of the color light colors is approximately between this 380 to 740 nanometer. And usually for the calculation of the limit of resolution of a microscope, a mid value approximately 580 nanometer is taken as the wavelength of the white light, which is used for the illumination of the object. And then the other factor for which calculation of the limit of resolution is the NA, that is the numerical aperture. It is defined as the light gathering capacity of the objective lens. Numerical value can be calculated of this numerical aperture can be calculated from the relationship that is NA is equal to N sine alpha, where this N is the refractive index of the medium between the specimen or the object and the objective lens of the microscope. And the multiplication between this value and the sine value of alpha gives the numerical aperture of this one objective lens. And then this alpha is the semi-angle subtended by the extreme ray coming from the, like this one, coming from the this an object, and which is collected by the objective lens. This alpha value ranges between this -1 and this one +1. The maximum value of alpha, this one sine of alpha, can be +1. But that's when these values are substituted, corresponding values are substituted in the original this one equation, k lambda and sine alpha, or NA, it becomes in 0.61 into 580 nanometer divided by n, or 1 plus 1 into 1, because we are taking this one this one value of n, that is the refractive index of the air. If there is no medium is introduced between the specimen and the objective planes, then it will be, the medium will be air, and the refractive index of air is taken approximately as 1, and that the maximum value of this sine value of alpha, it can be +1. Thus this maximum value is taken as 1, and the value of this limit of resolution of a light microscope now becomes that 353.80 nanometer. It means that two objects or 2 points or 2 lines which are separated by a distance of 3.53 nanometer can be identified by the light microscope as 2 separate points or 2 objects. But if the 2 objects are placed, or the distance between them are lesser than 353 nanometer, then they cannot be distinguished by the microscope as 2 separate points or 2 objects. But this one value of numerical this limit of resolution can be still reduced when we are using this 100x objectives, and we introduce the immersion oil between the object and the objective lens. When we are introducing the heat, this immersion oil has this one refractive index of approximately 1.55, and that is when we are taking this refractive index value of refractive index of this immersion oil 1.55, and using this 100x objective, then the NA value can be increased up to 1.6. That's when this NA value is replaced by 1.6, then the limit of resolution becomes this one 220 nanometer. And thus you say the light microscopes, their limit of resolution, the minimum limit of resolution is around only 200 nanometer. And it cannot be improved because it is governed by the wavelength of the illuminating ray. And that is because of this limitation in the, and another point is that the limit of resolution of a microscope is inversely proportional to the resolving power of the microscope. If the limit of resolution, the value of limit of resolution is smaller, then the resolving power of the microscope will be greater. And then, due to this limitation in the resolving power of the microscope, then the other types of microscope, especially the electron microscope, have been developed during the early 20th centuries. And the other group of microscope, that is the scanning probe microscopes, which examples being the atomic force and that is one scanning the Helen microscope. They have been developed in the late 20th century. And then when we again coming to the light microscope, the light microscope we will be discussing on the lens systems of the microscope. A compound light microscope has 3 lenses. It has a lens system having 3 individual lenses, that is the objective lens, then the ocular lens, or which is also known as the eyepiece, and the condenser lens. Objective lens is placed nearest to the object or specimen to be seen, and the ocular lens is nearest to the observing eye, while the condenser lens is nearest to the source of illumination in the compound light microscopes. Here we are just showing the position of the this one different lenses. This one lenses, individual lenses in the lens system of a compound light microscope. It is the ocular lens. Then this is the objective lens. This is which is nearest to the object or specimen. Then it is the condenser lens, and it is nearest to the source of illumination, light source. Then we are discussing about the functions and the different types of these lenses of a compound microscope. Then we are coming to the objective lens. Then there are 3 important functions of the objective lens. That is, it gathers both this direct and oblique rays coming from every point of the object, and that these direct rays they are to be combined or unite at the image plane to form corresponding image points. And in totality, thus this objective lens will form the first image of the object. And this image is to be magnified. And this magnification should be correspondingly, again, shall have the proper resolution so that it can be identified, or the details of the magnified image is identified by can be identified by the observing eye. Then when we are coming to the types of the objectives, there are usually three types of objective lenses are classified. That is the first one is the achromatic objectives, or which are also known as achromats. Then fluoride objectives, also known as the semi-apochromats, and apochromatic objectives, which are also known as the apochromats. These achromatic objectives, they are the simplest form of the simplest objectives with the least corrections for optical aberrations. And they are also least costly, and also they are the most widely used, most commonly used types of objectives. And they are corrected only for this one, chromatic aberrations in two colors, that is blue and red. And it is not corrected for spherical aberrations. And here, when we term this one optical aberrations, we can give a little discussion about these different types of the this one optical aberration very briefly. These optical aberrations or lens aberrations are defined as the defects in the image which are formed by a lens or by an optical system. And some of the most commonly encountered optical aberrations in microscopy are the chromatic aberrations. This chromatic aberration is a result of the fact that when a white light passes or is transmitted by a lens, by a glass lens, the different light rays having different colors, starting from violet to red, they are not focused at the same point. The light rays having the shortest wavelength, that is violet light, they will be focused nearest to the lens surface, while the light rays having the longest wavelengths, like this one, red light, it will be focused farthest from at a point farthest from the lens surface. That's the point. A point in this one object from which the reflected light, white light, is transmitted. If it is transmitted through the lens, then when they are united after passing through the lens, then they will not be united to a image point, but it will form a short diffraction spectrum. And this aberration or this defect in image formation of a point object to a point image is known as chromatic aberrations. And then this one type of this optical aberration or lens aberration is a spherical aberration. And this aberration is associated with the curved surface of the lenses. And it can be explained in such a way that when the light rays coming through this one curved surface of the lens, the light rays which are coming from the periphery of the lens and the light rays coming at the central part of the lens, again they will not focus at a point after passing through this one lens. The light rays coming from the edge or the periphery of the lens, they will focus nearer to the lens surface, while those light rays coming from the central area of the lens, they will focus farther from the lens surface. And this defect in the image formation by a lens is known as the spherical aberration. And thus, these objective lenses, they are manufactured to correct different types of these optical aberrations, lens aberrations, to avoid these lens aberrations and to form more perfect images when they are observed through these objectives and this one optical lenses. And these optical lenses and ocular lenses, these ocular lenses also, they are also corrected for this one, these types of optical aberrations. Thus, this achromatic lenses, they are only corrected for the two wavelengths, that is blue and red, and they are not corrected for these spherical aberrations. Then the fluoride objectives, they are manufactured from very advanced type of these glasses, and such as which has this one elements like fluorspar or fluorides, or more advanced type of synthetic glasses or substitutes. And this one achromatic, this one semi-apochromates or the fluoride lenses, they are more corrected for optical lenses in comparison to the achromatic lenses or achromates. They are also corrected for this one chromatic aberrations for blue and red wavelengths, and also they are also corrected for this spherical aberrations into this one light wavelengths, that is blue and green wavelengths. They are more this one costly than the achromates, and these fluoride lenses, they are not suitable for this one use in fluorescent lens fluorescent microscopy, because they usually have some fluorescence for in this one in the lenses itself. Then the third type of the objective, that is the apochromatic objectives or the apochromates. They are the most advanced, the most highly corrected types of objectives, and they are corrected for 4 colors, that is deep blue, then blue, green, and red colors in as far as this one chromatic aberrations are concerned. Means They are corrected for 4 colors in chromatic aberrations, and they are also corrected for this one spherical aberrations for 2 or 3 this one light wavelengths, especially this one blue and the red. Under this, the last one, that is apochromatic objectives. They are the most appropriate this one objectives for color photomicrography. And then when we are discussing about this objective lens, on the body of the objective lens, there are values and this one words which are engraved on the body of the objective lens, and they have different significance. This engraving of this one objective lens. Here it is the type of the objective that is, it means that you plan apo means it is means the type of the objective is a plane apochromatic, and here it is the magnification value, that is the magnifying power of this objective is 100x, 100 times, and it is the oil immersion or water immersion type. That is, when we are using this one 100x this one objectives, then it is essential to use this one oil immersion, to introduce this oil immersion between this objective lens and the specimen. And then here it is also essential that the thickness of the cover slip or cover glass, it should be this one 0.17 mm in thickness. 0.17 thickness. It is a mandatory to use this type of this thickness of cover slip when we are using this one, the objective lens of having the magnifying power of 100x. Then here it is given this numerical aperture of this objective lens, the value of numerical aperture, and then here is a color band. Here magnification indication of the color band. Different this one magnification, different colors are given for different magnifying power of the objective lenses. When this color in the color band is red, and then it is the magnifying power of the objective lens is a 4x. When the color is yellow, then it is a magnifying power of the 10x, and when the color is green, it is a 20x, and when the color is blue, then it is 40x or 60x, and when the color is white, the magnifying power of this objective is 100. Thus, these engravings on the body of the objective lens also give us the information about the objective lens, and what can means identify which type of objective lens is the magnifying power of which power of the objective lens is, and then also the thickness of the cover glass to be used, whether we should use immersion oil or not, and the value of the numerical aperture of the objective lens. All this information can be obtained from these engravings on the body of the objective lens. Then we are coming to the ocular lens. These ocular lenses, again, ocular lens has three important things. Hello. Hello. Sajasagupta.
Sir, please continue.
It is audible.
Yes, yes, audible, sir. A little bit. Please continue, sir.
And then
It
we are
is
coming.
audible, sir. Please continue,
Yeah.
sir.
When we are coming to this one, functions of the ocular lenses, this ocular lenses, they have three functions. Then the first function is to deliver the object image which is formed by the objective lens to the observing eyes or the other recording devices like this photographic plate. And then it further magnifies the image formed by the objective lens. The image formed by the objective lens is already magnified, and this magnified image is again further magnified by the ocular lens. Thus, as we have already discussed, the final magnification of the object image is equal to the multiplication result of the magnifying power of the objective lens and the ocular lens. And then these ocular lenses, they also correct some of the optical. It is here. This one here. It is not observations. It is aberrations. Means it also corrects some of the optical aberrations. And then there are two types of ocular lenses, that is negative eyepiece, or it is also known as Huygens eyepiece, and the positive eyepiece, or the Ramsden eyepiece. The negative or the Huygens eyepiece, it uses two lenses. The upper lens is known as the eye lens, and the lower lens is known as the field lens. And in their simplest form, or the simplest setup of this Huygens or negative eyepiece, both this eye lens as well as the field lens, they are plano-convex lenses. And both these lenses, the eyepiece, eye lens and the field lenses, they are convex lenses. They are oriented towards the specimen. And this type of eyepiece, that is a negative or Huygens eyepiece, is mostly used in Singh and this one laboratory microscopes, or laboratory Singh and laboratory Singhs. And if if you find any ocular or eyepiece without any other engraving, only giving this the magnifying power, then it is most probably a Huygens or negative eyepiece or ocular. Then the second type of eyepiece, that is positive eyepiece or the Ramsden eyepiece, it also uses two lenses, that is eye lens and the field lenses. But for for more correction of this optical aberrations, this two individual lenses or lens elements, that is eyepiece, eye lens and the field lens, they are cemented. They can be cemented together as a single lens element. And then In this case also, these two different lenses, that is eye lens and the field lenses, both of them are plano-convex lenses in this one. Ramsen eyepiece also. In Ramsen eyepiece, they are used for this one. They are more advanced and more corrected for the optical aberrations, and usually they are used for this one research microscopes. And then when we are coming to this one, the condenser lens, there is a one function of the condenser lens, that is, it has to collect the light rays from the source of illumination, and it has to focus the light beam into the object plane so that it can illuminate the object. And this condenser lens does not have any role in image formation. However, the intensity of the illuminating light ray is controlled by the condenser lens. And a proper assessment of the condenser lens and a proper assessment of the illuminating ray is important to get the sharpness and the depth of focus as well as contrast to the image formed by the microscope. And to some extent, the depth of focus and the contrast of the image is enhanced or increased to a reasonable level by greater intensity of the illuminating ray. Then there are three types of condenser lens in light microscopy. That is the four types of condenser lens. That is the AB condenser. Then the second is the Airplanetic condenser. The third is the Apochromatic condenser, and the Airplanetic, Achromatic condensers. This AB condenser is the simplest type of condenser and also least corrected and the most widely used condenser. And it is not corrected for this one any type of this optical aberrations. And usually it has two lenses, and to have this or to give a higher value of numerical aperture, this AB condenser may have this one may be associated with more this one lens elements, that is more than 2 lens elements. It may contain 3 lens elements to give a higher value of numerical aperture of the condenser. Then Airplanetic condenser, it is corrected for spherical aberration, but not for achromatic aberrations. We have already discussed about the optical aberrations, about this one achromatic aberration as well as the spherical aberration. And this Airplanetic condenser is not corrected for this one chromatic aberrations, while it is corrected for this one spherical aberrations. They have more number of lens elements, which may be up to 5 lens elements, individual elements. These Airplanetic condensers are capable of producing excellent result images in black and white. This one photomicrography using this green light illuminations. Then the third type of this one condenser lens is the achromatic condensers. These condensers, they are these condensers are Cristo, parce que non tàu le protector là cả tàu tôi làm thuốc thì cái gì nào xin chào tôi làm thuốc rồi này ai sẽ cái nào sẽ thôi là các bạn. These achromatic condensers, they are corrected for this one chromatic aberrations, but not for this one spherical aberrations. They are corrected for this one chromatic aberrations in two light waves, that is blue and red, and also they also can be used for this one black and white. It's a black and white photomicrography, right? Then the last one, that is the Airplanetic chromatic aberrations. It is the most corrected form of this one condenser lens, and in this type of the condenser lens, it has the highest level of correction of the optical aberrations, and it is corrected for both this one spherical as well as the chromatic aberrations. And the number of the internal lens elements of the airplanetic chromatic condensers may be up to 8 lenses according to the image quality, desirable image qualities produced by the this condenser lens, and they are usually used for this research microscope, and they are excellent or the choice of this one condenser type, which is used for this one critical color photomicrography. Yeah, and this is up to this one. We have already discussed this one about the basic principles of this one microscopy with the special basis on light microscope, and thank you to the organizers, and also thank you to the participants of this webinar. And if there is any some explanations or queries, then it can be explained, or if there is any queries, then it is welcome. Hello, sorry. Thank
you, Professor Shyamkesho, for talking about the different types of microscope and its resolution power, function of condenser lens, and types of lens. Now, I request Professor Asa Gupta, President and Convener of National Sakti, to give her presidential speech.
Honorable Professor Shyamkesho Singh, Department of Life Science, Manipur University. Participants are present here, especially I mention Dr. Surekha Kalkar, Head Department of Botany from Institute of Science, Nagpur. Dr. Anandita, she is from Christ Church College, Kanpur. Professor Naveen Ambas, she is also from Christ Church College, Nagpur. Dr. Shashti Agarwal, she is from Janta College of Education, Chandrapur. Our participants, members of Shakti, and students. It's really very heartening to listen to Professor Shyamkesho Singh, his wide experience, and the way lucid way he explained the principles of microscopy. Sir, you have talked in detail about the different aspects of microscopy. You talked also how the new type advances are there over the light microscopy. You have compared them and the differences you have pointed out. You begin with the definition of microscope, that it is optical instrument, produces highly magnified image and uses lens or combination of lenses. You have talked about new advances of scanning probe microscopy. You have talked about atomic force microscopy, scanning tunnel microscopy. You have talked about the classification of microscope and started with the source of illumination that our eye, for example, 380 to 750 nm, which is visible light spectrum. And this is used by light microscopy, and electron microscope, it uses the electron beam as a source of illumination. You talked about the working principles of bright field microscope, dark field microscope, fluorescent microscope, and electron microscope. You talked about formation of image, magnification, and resolution of magnified objectives that by the light microscope. You have talked about the limit of resolution. Then you have talked in detail also about the lens systems of light microscope. Very beautiful and very detailed, because I think all must be that the students, they are really grateful to you. We are all grateful to you for pointing out so many details, because generally we know the compound microscope, we are using it, we don't know the so many details which you have pointed out very beautifully of the objective lens, ocular lens, and condenser lens, their types and functioning, how to correct.
Thank you, Professor Asagupta. Now I request Dr. Sorokabam Ibechawi of Petrogi College to propose board of
Thank you, Dr. Biteshwari. First of all, I thank Professor Mutum Shyamkesho Singh for his valuable lecture on the basic principles of microscope, which is also very useful for the graduate students, and not only the graduate student, it also refreshes all the participants, where the knowledge has to be known in details about the microscope. Though we applied it without knowing the details, we cannot handle the microscopes properly. Sir has so much detail on the this topic, and Madam Sagupta has also give a nice summation on sir's topic. So thank you, sir, for sparing your valuable time and giving such a knowledgeable and valuable lecture. Next, I thank Professor Asagupta, who is a convener of Manipur Shakti and SEED, for organizing such a meaningful webinar series in the observation of Science Week Observation 2021. And she is also busy in arranging different lectures from the different experts to the participants. And not only this, I also thank the program officer Santosh, who is busy providing this e-platform to all of us, and to all the participants from different institutes and institutes and colleges from different lecturers, etc., for participating to this webinar, a successful webinar series. So I thank you, all the participants who is from Manipur and outside Manipur, and many experts who is also participating here. So I thank all the participants once again. Thank you all for making this webinar successful. So Biteshwari, should I close the webinar or?
Let's close it here.
Okay. So with permission from the chair today, I close today's webinar series. So thank you once again to all the participants, and thank you once more, Sir Shyamkesho.
Thank you.